Hey class, it is Monday, and while I have your attention right away, I wanted to give you a heads up that you are going to have a quiz tomorrow over lessons 5 day 2. So this second half of 5, solving equations by factoring. So make sure you have this textbook assignment done for tomorrow. And then it's also going to be a big chunk over 5.6. So make sure you have this textbook assignment done tomorrow. And then also 5.7. So make sure this assignment's done for tomorrow. And my sub on Thursday, I believe, told me that a lot of you had all your homework done during that class period. So it sounds like you guys are pretty caught up. So I expect everybody to have that ready to turn in tomorrow. I did make an optional quiz review worksheet right here. Um, it's just some extra practice and what you can kind of expect to see on the quiz. So, solving polynomial equations by factoring. There is one kind of like more difficult factoring question on there. If you're given a factor of a polynomial, find the other factor. So, how we do that with synthetic division. And then given the zeros, write the equation. And then there is one like application problem similar to this one. So I will post an answer key to that quiz review soon. I just wanted to point out that if you want the extra practice, these would be some good problems to do. And I believe my sub should have that printed out for you. Okay, we are going to start the 5-8 notes right now. I'm probably going to try to keep this short because I would prefer to teach this in person, but we need to at least start it here because I've missed a lot of days. So let me switch over to my tablet mode quick. Okay. So we're going to start with this ACT style type of warm-up problem. And I'm actually going to give you guys 1 minute to try this, similar to the speed you need for the ACT. So I'm going to set a timer on my phone and I'm going to give you 1 minute to try this starting now. Time's up. That goes by fast, doesn't it? You can draw a picture here if you want to. It's not super helpful, but we know it has an area 32 square feet and a perimeter of 24 feet. You could definitely probably guess and check too until you found an answer here. That would be a problem solving strategy, but I'm just going to call the width of this x and the length is y. So here's what we know. We know the area, which I could find as x times y, is 32 square feet. And we know the perimeter, which I would have 2 x's and 2 y's. Perimeter is the distance around the outside, so that total distance is 24. So we have two equations with two variables. So I'm going to use classic substitution here. So what I'm going to do is I'm going to solve this red equation. I'm going to solve it for y. So move over the 2x, divide by 2. And then I'm going to substitute that in for y. We did problems like this when we did quadratics in chapter 4. Because what ends up happening here, when you substitute that in for y, you'll see we end up getting, so I'm going to distribute here, I get 12x minus x squared, end up getting a quadratic. degree 2 polynomial equation. So I would try to factor and solve this. I'm going to set it equal to 0. So I'd add over that x squared minus over that 12x. Then I have that 32. This one's a nice quick one to factor. Two numbers that multiply to 32, positive 32, and add to negative 12 would be negative 8, negative 4. So this would give us solutions of 8 and 4. So if you're like, well, what the heck? Would it be 8 or would it be 4? And notice by plugging like both those solutions in, y is just going to be 12 minus whatever x is. So if we let x be the 8 solution, y is 4. If we let x be the 4 solution, then y is 8. So that's just saying y could be technically your length or your width. So to answer their questions, which is the shortest of the side lengths, that would be 4. J. Okay, that doesn't really have to do with our lesson, but has to do with the ACT. Good review from chapter 4. Really good Algebra 2 style type of ACT problem. Okay, so we're going to explore a little bit on this graph, but today we're going to talk about something called the rational zero theorem. So here's kind of where it comes from, a little discovery. So you can see here, I have one turning point here. So this is at least a degree 2 polynomial functions, and I see two x-intercepts here, so I know it has two real solutions. That doesn't mean it is necessarily degree 2 with only two real solutions, but it could be, and it's at least a degree 2. Okay, so if I were to write this as my zeros here, I have one at 0.4, which that as a fraction is 4/10, which reduces to 2/5. I have a solution of x equals 2/5 is if this were a part of an equation. And that's what we're going to do here is we're going to write the equation and see how it relates to these zeros. So then my other zero, that 1.5, that as a fraction is 3/2. Improper fraction. Okay, so we're going to kind of do like that method where we work backwards and write these as factors. So if you were to kind of like picture a factor and setting it equal to 0 and getting x equals 2/5 as a solution, you'd be like, what type of factor did that come from? We can kind of just like undo the algebra here. So instead of dividing by 5, let's times both sides by 5. And we get 5x equals 2. So I'm kind of undoing this and putting it equal to 0 and then minusing over the 2. And I'm like, aha, this x equals 2/5. That solution came from somebody setting 5x minus 2 equal to 0. So I know that 5x minus 2 is a factor. Okay, we're working backwards. That would give us this 0, that 2/5. So similarly with the 3/2, let's kind of undo that. We get 2x equals 3 minus over the 3. You're like, oh, 3/2. That came from somebody setting 2x minus 3 equal to 0. Okay. Now, I don't know if this is my exact equation. There could be some a factor, but I know that this was set equal to 0 at some point. So when I say there's an a factor, there could be a number there, but it wouldn't matter because when I set this equal to 0, I would get these two solutions. Okay, so what we're going to do is we're going to multiply this together, just kind of like we did before. So that'd give me 10x squared minus 15x minus 4x plus 6, or you could add those two inside ones together at once if you wanted to, but we get to, oops, forgot to actually add them. We get to here. Okay, now here is what I want you to note. So we had these solutions. Let me go back here to the 2/5 and to the 3/2. We had these solutions, and let's look at our numerators of these. These are both, I should point out, these are both rational solutions, right? They can be written as fractions. They're not irrational. Irrational would be never-ending decimals like pi that go on forever, but they're rational. And if I look at the numerators of these fractions, the numerator in the first solution is 2. The numerator in my the second solution is 3. And if you look here at this number 6 in our answer, that contains factors of the numerator of our 0, 2, and 3. Okay, so you're like, okay, this feels like a stretch. It's probably just a coincidence that those numerators were factors of that constant term. But then if you look at the leading coefficient here, this 10, and if you look at the denominators, 5 and 2, you're like, oh, well, that worked for that. Those would also be factors. So this contains factors 5 and 2. So in both my rational solutions, the denominators were factors of the leading coefficient of where those zeros would come from, and the numerators were factors of the constant term of my equation where this came from, and that's not a coincidence. That is the rational zero theorem. Remember, guys, if I ever go too fast through the videos, you can always pause them, rewind them, do what you need to. So this rational zero theorem, they use P's and Q's, and basically you can find every possible rational zero by finding the factors of your constant term. So we call that one our P. And then Q is our factors. Oh, let me use a different color here. And Q is our factor of the leading coefficient. So in my little example here, well, they have an example in that theorem, but I'm going to do a different one here. In my example, 10 is my leading coefficient and 6 is my constant term. So how I kind of show my work for this is I say my P, I usually start with my P. My P is 6 and my Q is 10. So this rational zero theorem says you can take all your factors of your constant term. So let's list all my factors of 6. So those are numbers that multiply to 6. I'd be like 1 times 6 and 2 times 3. And that's it. 1, 2, 3, and 6. And then all my factors of my leading coefficient. So my leading coefficient in this case was 10. Factors would be 1, 2, 5, and 10. Those would be my only factors of 10. So what I can do is I can create a list of all my possible rational, so again, this doesn't include irrational, this doesn't include imaginary, all rational zeros by taking all my factors of P and divided by all my factors of Q. Okay, so the other thing that goes along with this is it can be the positive version or the negative version of the number, so we start with plus or minus. So what I do is I kind of just start with my first factor of P, so I'm going to start with the 1, and I take 1 and I divide it by all the factors of Q. Okay, so do this with me here. I'm going to do 1 divided by 1, which is 1. 1 divided by 2, which is 1/2. So you'll notice I'm doing plus or minus every time. 1 divided by 5, which is 1/5. And then 1 divided by 10, which is 1/10. Those are all possible rational zeros of this degree 2 polynomial function. Now I'm not done. I only used the 1. Now I'm going to move on to the 2 and do the same thing. Divided by all my factors of Q, which in this case is 10. So 2 divided by 1 is 2. Now 2 divided by 2 reduced is 1, and that's already on our list, so we don't need to list it again. 2 divided by 5 is 2/5. 2 divided by 10 is 1/5, and that's already on our list. Okay, 2 is done. You can kind of cross them off as you go if you'd like. Next up is 3. 3 divided by 1 is 3. 3 divided by 2 is 3 halves. Notice how I'm just separating them with a comma. 3 divided by 5 is 3 fifths. And 3 divided by 10 is 3 tenths. Good stuff. Okay, last one here is 6. So 6 divided by 1 is 6. 6 divided by 2 is 3. That's already on my list. 6 divided by 5 is 6 fifths. And then 6 divided by 10 is 3 fifths, and that's already on my list. So this right here, folks, this is the rational zero theorem. These are all possible rational zeros. So you're like, that's a pretty long list. And you're right, it is. But we know some possible rational zeros that are not zeros, such as like the number 14. Wouldn't be a possible rational zero. And all this kind of does is it kind of just helps us narrow down our options for which zeros we want to test synthetically to see if we indeed get out 0. Okay, let's try one more of those. List all the possible rational zeros of the function. All right, so again, I start by identifying what my p is, and that's my constant term, which in this case is 4. My q is my LC, my leading coefficient is 3. Then you list their factors. So the factors of 4 are 1, 2, and 4. Factors of 3 are 1 and 3. And then to create your list, you take all your p's divided by all your q's. So I like to start with 1. 1 divided by 1 is 1. 1 divided by 3 is 1/3. Okay, that one's done. Moving on to 2. 2 divided by 1 is 2. 2 divided by 3 is 2/3. 4. 4 divided by 1 is 4. 4 divided by 3 is 4/3. Okay, we had no repeats that time, so that right there would be all my possible rational zeros. That list isn't so bad. All right, if you're confused, folks, where I'm getting these numbers, don't worry. I'm going to be back tomorrow, and we will get this all cleared up. Don't you worry. Let's try another type of problem here. Find all zeros of the function. You can use Desmos to suggest what to try to save time when you have a long list. Okay, so I do have a degree 4 polynomial function, and remember, when I'm asked to find zeros, that's really asked me to find x-intercepts, so I'm plugging 0 in over here. Let's start by making our list of possible zeros. So my p's and q's, that's what I tell my students. Find your p's and q's. P is 30. And q, my leading coefficient, is 1. I love it. 30. Lots of factors. 1, 2 is a factor. 3 is a factor. 4 is not. 5 times 6. And then I just kind of do their pairs. 3 times 10, 2 times 15, 1 times 30. My only factor of 1 is 1. So my p's over q's list is going to be pretty easy this time because I'm just dividing everything by 1. 1 divided by 1 is 1. 2 divided by 1 is 2. Don't forget plus or minus in front of all these. That's part of the rational zeros theorem, as it could be the positive or negative version of all these. 3 divided by 1 is 3. 5 divided by 1 is 5. 6 divided by 1 is 6. 10 divided by 1 is 10. 15 divided by 1 is 15. 30 divided by 1 is 30. Okay. So basically from there, folks, we're going to use synthetic division and just guess until we find one that is a 0. So using the remainder theorem, we want to get a remainder of 0. Now, we can use Desmos to help us. So let me pull up Desmos here. And you can do this on your homework. 2. So we have our function here, x to the 4th plus x cubed minus 19x squared plus 11x plus 30. And sometimes you might have to zoom out a little bit. In this case, I don't. I can see all my zeros here. I'll click on them. I have -5, -1, 2, and 3. Nice. Those are all on my list, right? -5 was on my list, -1, 2, and 3. They're all rational zeros. So we're just gonna pick one. I'm just gonna pick -1. I tend to pick like 1 and -1, 2 is another one I pick. I try to pick smaller numbers because they're just easier to work with. So I see here -1. You just, like I said, have to pick one. We're gonna use that one as our first test. So yes, back to tablet mode. So you're gonna set up synthetic division. And again, you're going to pick one that you saw in Desmos. So we saw -1. Okay. So just like we've kind of been doing, this is a good review for the quiz. We're going to use the coefficients from the original polynomial. So that'd be 1, 1, -19, 11, 30. And what we're looking for is that remainder of 0. That will show that it is a 0. Now we just saw Desmos, so we know this is going to work. But bring down the 1, multiply, add, multiply, add, multiply, add, multiply. Aha, it did work. Okay, we know that is a 0, which means x plus 1 is a factor. Okay, so the reason we do this synthetically, and I explained this a couple times, is because not only did we find a 0, but we also simultaneously factored out x plus 1. So since this started off as a degree 4, this is now going to be down to a degree 3. So it'd be x cubed, no x squared term, minus 19x plus 30. Okay. So then we're left with this. And I know there's 3 terms, but we don't know how to factor this because I have that x cubed and not x squared. So what we're going to do is we're going to do synthetic division again. So we'd go back to Desmos and pick another number. Now we just did that, and I know one of them was 2, so I'm going to use 2. And I'm going to use these blue numbers to try to break this down further. 1, 0. You could actually use the numbers right from here. 1, 0, -19, 30. And again, if all is good, we should be getting a 0 as our remainder. So let's see if we do. Bring down the 1, multiply, add, multiply, and multiply, add. Bingo! All right, we got 2 zeros. So x plus 1 from the first round. 2 would come from x minus 2. And now I'm left with a degree 2 x squared plus 2x minus 15 equals 0. And we are left with something we know how to factor. There are 2 numbers that multiply to -15 and add to +2. That'd be +5 and -3. And then you got these factors from Desmos that we found from the zeros. Okay, folks, so there is this expression factored. You just factored that. That factored is this. Now to finish this, we gotta solve. So we get -1, which again, that's what we found right here. 2, which is what we found here. And then x minus 3 would give us 3. If you need to set these equal to 0 to see this, you can. And then we get -5. Now let's go back to our graph and see, were those the zeros? -5, -1, 2, and 3. We did it. Good job, guys. Okay, we're just going to do one more problem and then we'll stop there. So this one's the same idea, a little bit trickier. So I'm still trying to find the zeros. But if you look here and you start your P's and Q's list, you're like, wait a minute, I don't have a P. But actually, what you notice here is they have a GCF. They have a GCF, which is X. So let's go ahead and factor out the X. And now, if you want to right away, set these each equal to 0. X could be 0. That's going to be an x-intercept on our graph. That's a 0. And this, which does not factor by grouping. You can try, but it doesn't work. This could also be 0. So we have the solution. I'm going to box it in red here. So remember, that's going to be part of my solution. But this, I'm going to have to do my P's and Q's and do my synthetic division to factor this. Okay, let's do it. P is 28. Q is 5. Okay, so rational zeros theorem, our big takeaway from today, says list the factors of 28. So you got 1 and 2. 3 is not a factor. 4 times 7. 2 times 14 and 28. Factor the 5 are just 1 and 5. So to make our list here, take all your P, divide them by all your Q's. All right, 1 divided by 1 is 1. 1 divided by 5 is 1/5. 2 divided by 1 is 2. 2 divided by 5 is 2/5. 4 divided by 1 is 4. 4 divided by 5 is 4/5. If you're asking, do we really have to list these all out? The answer is yes. 7 divided by 1 is 7. 7 divided by 5 is 7/5. 14 divided by 1 is 14. 14 divided by 5 is 14/5. 28 divided by 1 is 28. 28 divided by 5 is 28/5. So again, what you would normally do here is do synthetic division and just keep guessing until you find one. But again, to save time, we're going to use Desmos. So I want to go back to that. Okay, here's my new one. Typing in the whole thing, the original function. Okay, so yeah, you might have to zoom out a little bit. What's kind of going on here? Look at the end behavior too. All this stuff we've been talking about is a degree 4, positive leading coefficient. Look, my ends are going up. Okay, so here's that 0 at 0 that we found right away. And now this one is at 0.8. And you're like, wait a minute, this is a degree 4. Why are there only 2 x-intercepts? We'll get to that in a second. Because that's great thinking. You're thinking fundamental theorem of algebra. So we got 0.8, which that is a fraction. 8/10 is 4/5. 4/5, that's still a rational zero. I know it's in a whole number, but that's going to be our magic number here that we will start with. Our synthetic division. Okay, now remember we are using these because that is what we're trying to break down, not technically the original because we had to factor out that x. So you got 5, negative 29, 55, negative 28. Okay. Bring down the 5 times 4/5, that's 4. Add negative 25 times 4/5 is negative 20. Add, that's 35 times 4/5 is 28. Add, ding, 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 we get 0. Okay, so that x equals 4/5. If you have to work backwards, times both sides by 5, minus over the 4, that comes from 5x minus 4. And now I'm left with a degree 2, 5x squared minus 25x plus 35. Okay, so right now we have zeros at 4/5 and 0. And you're like, well, that's all I saw on my graph, which means the other two have to be imaginary, if you guessed it. So this right here, folks, if you are trying to factor this, that's great. That's great algebra skills. But it's not going to factor because the other two solutions are imaginary. You could divide both sides by 5 to make your number smaller. That's fine. But you're going to have to use the quadratic formula or complete the square from here. I'm going to do the quadratic formula. X equals the opposite of b plus or minus the square root b squared minus 4ac all over 2a. Okay, so we get to here, and underneath the radical, I got -3, which that's starting to make sense, which, using imaginary numbers, that'd be √3i. And for my final answer, I want to break this up. So 5/2 plus or minus square root of 3 over 2i. Okay, there we go. Now, again, fundamental theorem of algebra says whatever degree, and you should be paying attention to this, whatever degree polynomial started with, that's how many total zeros you should have. Counting imaginary, counting rational, counting real. So we have 1, 2 real, 0 and 4/5, and we have 2 imaginary, 5/2 plus √3 over 2i, 5/2 minus √3 over 2i. And remember, those imaginary numbers always come in pairs. That's the conjugate complex theorem. So everything is making sense. Okay. For the rest of class, I want you working on some of the homework that's due tomorrow for your quiz. Again, I repeat, quiz tomorrow. Or I want you to start working on that optional quiz review worksheet. For 5/8, I believe there is a book assignment and a worksheet, maybe? I don't know. We'll finish the 5/8 notes when I come back, either tomorrow after the quiz if we have time, or if not, Wednesday. No worries. But I will see you guys soon. Let me know if you have any questions.